Rain. Whether you're a farmer or a pedestrian, you want to know if it'll rain tomorrow or not. But can we get any wiser about it? So far, I've only looked at repeatable independent trials with binary outcomes, i.e. success and failure. By thresholding the amount of precipitation, we can still be looking at binary outcomes, rain or not rain, and we can still contemplate repeatability. But we're now going to consider a model where the trials are no longer independent. I'm doing this in honor of Bruno the Questionable, who wanted me to look at such a case. In the short run, the weather is of course not independent. Approximately, the weather is the same now as it was 1 second ago. I'm not going to use that information though. I'm just going to check if there's some dependence from one day to another using a dataset. And if there is, I want to take a closer look at the model that incorporates it. Since I want to check for dependency, I need at least one model that assumes independent data, and that's my trusty old friend from previous clips, which I've called the free binomial model, and which I'm going to assume you are familiar with by now. Now, the alternative model should have some kind of dependency. Let's call the state of day I xi. So if xi is equal to 1, day number I is rainy, and if it's not rainy, xi is equal to 0. In general, you can use the rule of conditional probability many times to find that the probability for a given set of consecutive outcomes, x1, x2 and so forth up to xn, is the probability of x1 times the probability of x2 given x1 times the probability of x3 given x1 and x2 times and so forth the probability of xn given x1 to xn minus 1. But in this general case, the model complexity increases with the number of data, and you will not get any wiser about the model. A model's prediction strength is what determines the posterior model probabilities, so we need more structure than this. Markov chains are one way out of this mess. In a Markov chain, the outcome of a trial only depends on what happened previously through the closest measurement. The probability of xn given x1 to xn minus 1 is equal to the probability of xn given only xn minus 1. And if you have 3 trials, x10, x11 and x12 for instance, you've got that x10 and x12 is independent condition on x11, see clip 13, evidence about evidence. Also the 5th clip in the YouTube religious identity survey videos can be useful. We can give a graphical impression of the model by making a large chain of arrows from one measurement outcome to the next. Each measurement influences the next, which again influences the next, and so forth. The probability of the dataset is thus the probability of x1 times the probability of x2 given x1 times the probability of x3 given x2, and so forth up to the probability of xn given xn minus 1. Now this is still fairly complicated until we start to put even more structure on it. As I said, I still want to consider repeatability, so I'm assuming that the probability of rain given rain the previous day is the same for all days, which is called stationarity in Markov chain language. I can now label the probability of rain given rain previously for P1 and the probability for rain when it didn't rain the previous day, P2. In a sense, this is the same setup as in the previous clip, where I considered outcomes taken from 2 different sources. In this case, the 2 sources are the measurements with rain the previous day and the measurements with no rain the previous day. If there's no dependency, the success rate, i.e. the probability of rain, should be the same no matter what happened the previous day. But what about the first measurement? We don't have a previous measurement to condition on for that day. However, with the probability of rain given rain the previous day and given no rain the previous day, I can calculate the unconditional probability of rain using rule 6. The probability of rain in day I is the probability of rain on day I given rain on day I minus 1 times the unconditional probability of rain on day I minus 1 plus the probability of rain on day I given no rain on day I minus 1 times the probability of no rain on day I minus 1. Using stationarity and labeling the unconditional probability of rain P marked, we find that P marked is P2 divided by 1 minus P1 plus P2. For the rest of the data I have K1 out of N1 cases of rain with rain the previous day and K2 out of N2 cases of rain with no rain the previous day. The data likelihood for day 2 to day n under this model will be p to the power of k1 times 1 minus p1 to the power of n1 minus k1 times p2 to the power of k2 times 1 minus p2 to the power of n2 minus k2. If it rained the first day, we multiply this with the unconditional probability of rain p marked, and if not, we multiply with 1 minus p marked. Getting data about rainy days is something you can collect for yourself, but if you want a lot of data, it's better to go to a meteorological institute like I did. There I got a set of daily measurements of precipitation for 10 years. I then thresholded it at 5 millimeters of rain. With this data I got a total of k equal to 596 rainy days out of a total of n equal to 3652. When I want to process this in the Markov model, I also need to know that the first day had no rain, that for days with rain the previous day we had k1 equal to 202 rainy days out of n1 equal to 596. While for days without rain the previous day, we had k2 equal to 393 days out of n2 equal to 3055 days. The data likelihoods under the two models is found taking the data likelihoods given the parameters times the prior probability of the parameters and summing over the possible values of these parameters. This yielded the following base factor for Model 1 independence versus Model 2 Markov chains. 2.32 times 10 to the power minus 29, i.e. the data is 4.3 times 10 to the power of 28 times more likely under the Markov chain model than under independence. So clearly there is dependency, meaning that the weather today is useful evidence for the weather tomorrow. We can also take a peek at the posterior probabilities for rain tomorrow given rain today and given no rain today. As you can see, the two distributions are a bit different. They are peaking around the observed rates, which are 33.9% for the days with rain the previous day and 12.9 days for the days where it didn't rain the previous day. Since there were fewer days with rain than without rain, the estimate for P1 is more uncertain than for P2. When we got dependence, we can also take a look at covariance, which I mentioned in clip 18. Covariance is a measure of linear dependency, and with binary single outcomes, covariance between two consecutive days is equivalent to dependency of the outcomes. So we can use covariance as a measure of dependency in this case. The covariance is the following expectancy from clip 18. Putting in our defined parameters and using the definition of expectancy, we find that the covariance is p marked times p1 minus p marked. Let's transform this a little. If we divide the covariance with the standard deviation of the two quantities we are examining, in this case the outcomes of 2 consecutive days, we got a quantity called the correlation. This is a nice transformation because correlation is scaleless and is always found between -1 and +1, with 0 being no linear dependency. If it's -1, there is perfect negative linear dependency between the two. If it's +1, there is perfect positive linear dependency. Now, since the correlation is a function of uncertain parameters, it too will be uncertain. but we do have the posterior probability of these parameters, which for my rainy day data yielded the following distribution of this quantity. It peaks around 0.2 and has 95% of the probability mass in the interval 0.16 to 0.24. Clearly the correlation is not zero, and this again is the same as saying that one rainy day makes another more probable. It is raining today. That's not all that surprising though. It was raining yesterday too.